Welcome to this deep dive where we try and take complex topics and, well, make them clearer.
Mhm.
Today, we're tackling something really at the forefront of network technology. It's the convergence of radio access networks, or RANs, and artificial intelligence.
Right. What people are increasingly calling AI ran.
Exactly.
And what's really fascinating here, I think, is the scale of this shift. We're moving beyond RANs that were just designed for communication
Right, the old way.
to a future where the network infrastructure itself is, well, an integrated compute and communication platform. Intelligent.
Yeah, you're used to your mobile network mainly as the pipe for your calls and data, simple connection. Now,
Mhm.
imagine that same infrastructure dynamically running sophisticated AI. So our mission today is really to unpack the technical side of AI RAN
Yeah, the nuts and bolts.
and explore its potential impact. We'll be laser focused, as always, on the technical details, the implications. No ethics today, just the tech to give you a really clear understanding of this evolution.
Sounds good. And at its core, AI RAN, it's about integrating those RAN functions, everything enabling your wireless connection with AI workloads, and crucially, on the same underlying hardware.
Okay, so not just layering AI on top.
No, not at all. It's a deep integration. The whole point is to seriously enhance network performance and really optimize how resources are used, better asset utilization.
And our sources suggest it's not just one single concept, is it? There are sort of three key flavors, three manifestations.
That's right. We're looking at AI for RAN, AI on RAN, and AI and RAN, each slightly different.
Okay, definitely need to break those down. But first, let's maybe trace the journey. How did we get here? What drove this convergence towards AI RAN?
Well, if you look back, traditional RANs, they were primarily designed for one thing, mobile broadband.
Right. Voice and then data.
And they did that job well for a time. But then came the explosion, the sheer number of connected devices, the increasing demands of applications.
Streaming, AR, VR.
Exactly. All of that really stretched the limits of those older architectures.
Hmm?
They just, they weren't built for that kind of capacity or the variety of uses we see now.
So the original design hit a wall. What was the sort of the interim step? How did the industry start addressing these limits?
Well, the industry saw the need for designs that were more flexible, more adaptable. You needed something that could handle a wider range of applications, different computational needs. Yeah. Bringing that computational power closer to the network edge,
Yeah.
closer to where data is generated and used.
Reduces latency, makes things more responsive.
Precisely. For many applications, that was a big improvement.
So edge computing helped, distributing processing power. How does AI RAN then take that concept even further?
So AI RAN builds directly on that edge foundation. It envisions taking that same edge infrastructure and running not just the essential RAN functions, but also various AI workloads. We're talking generative AI, large language models, LLMs,
Well,
all on the same shared resources. That fundamental convergence, communication, and computation right there at the edge. That's really what defines AI RAN.
that sounds like a pretty major shift, a
Yeah.
big undertaking. What are the key advantages? What's the real payoff for doing this deep integration?
The potential benefits are, well, they could be transformative. Think about zero-touch network and service management. ZSN.
Well, that's
Yeah, it implies a much more autonomous network, self-optimizing, self-healing with, minimal human intervention.
frees up resources, cuts operational costs.
Exactly. We also expect intelligent radio resource control, using AI to dynamically optimize how spectrum is used.
Which leads to better spectral efficiency.
Right, more data over the same amount of spectrum. Huge deal. And maybe the most intriguing bit, AI as a service.
AIs, powered by the RAN itself.
Mm-hmm.
So mobile operators could potentially offer AI processing as a service using their existing network footprint.
Precisely.
Yeah.
That's the idea. And the industry momentum behind this, it's undeniable now.
You can feel it building.
Yeah, there's this growing consensus around an AI native RAN for 6G, where AI isn't an add-on, it's woven in from the start.
Built-in intelligence.
Right. This communication compute convergence is foundational for that future. And we're seeing serious efforts in standardization to, pave the way.
You mentioned standardization. Which groups are really driving this?
Well, several key bodies. You've got the ITUT and ITUR, part of the International Telecommunication Union. They're setting requirements, recognizing AI as fundamental for next-gen networks.
Okay.
Then there's 3GPP. They handle the mobile standards. They're already adding AI features into 5G Advanced.
Right.
And the O-RAN Alliance, they're focused on open, intelligent RAN architectures, really pushing the integration of compute and communication.
And wasn't there a specific alliance formed just for AI RAN?
Yes, absolutely. The AI RAN Alliance.
Yeah.
Formed just in 2024.
Pretty recent then.
Very. It's a big collaboration. Operators, tech vendors, research institutions, all focused specifically on accelerating the innovation and the commercialization of AI-powered RAN. Its formation really highlights the industry's commitment.
Okay, that definitely sets the stage. We see the evolution, the drivers. Let's dive into those three manifestations you mentioned: AI for RAN, AI on RAN, and AI in RAN. Let's start with AI for RAN. What does that mean in practice?
So AI for RAN is all about using AI to make the RAN itself better, enhancing performance, efficiency, right down at the protocol and architecture level.
Okay, so using AI to tune the network's engine, basically.
That's a good way to put it. Using AI to intelligently optimize the inner workings of the mobile network.
Can you give us some examples? Where is this AI optimization being applied?
Sure. Down at the physical layer, the PHY layer, AI algorithms can do more precise channel estimation.
Which means?
It's like the network learning the wireless path better, so it transmits and receives signals more effectively. It can also optimize beamforming.
Directing the signal more accurately to users.
Exactly. Also, dynamic power adjustment, saving energy, reducing interference, and smarter interference mitigation. Those are key PHY applications.
Okay, that's the physical layer. What about higher up?
Moving up to the NC layer and beyond, AI can improve things like adaptive modulation and coding selection, choosing the most efficient way to encode data.
MCS selection, right?
Right. It enables dynamic resource allocation, load balancing across cells, optimizing multi-cell scheduling to coordinate transmissions better,
Yeah.
even enhancing mobility management.
How users move between cell towers smoothly.
AI can optimize all of that.
That's a lot of fine-tuning across different layers. It sounds like AI can really squeeze more performance out of existing radio resources.
Precisely. And this ties directly into network automation. RANs are getting more complex, more virtualized.
Harder to manage manually.
Exactly. So you need intelligence, agility. AI is crucial for moving towards that goal of zero-touch network and service management, ZSM.
ZSM, again, the self-managing network idea. How does AI actually help achieve that level of autonomy?
Well, AI models can analyze huge amounts of network data, historical, real-time.
Learning patterns, predicting needs.
Right. Based on that understanding, they can make intelligent decisions, proactively spot and fix potential issues, automatically configure the network, provision services, all with minimal or, ideally, no human touch.
Shifting from reactive fixes to proactive, AI-driven optimization.
That's the goal. It's a big shift.
Okay, that's AI for RAN, making the network smarter. Now let's pivot to AI on RAN. This sounds like the RAN infrastructure itself is hosting AI applications.
Correct. AI on RAN is about leveraging the compute power that's increasingly being built into the RAN infrastructure.
The edge computing power we talked about.
Exactly. Leveraging that to host and run AI applications directly. This creates a kind of symbiotic relationship, especially for things like smart cities, industrial IoT.
Where low latency and local processing are really important.
Yeah.
Symbiotic. So the RAN's connectivity helps the AI apps, and the apps provide value from network data.
Precisely.
Yeah.
And this opens up potentially very interesting new revenue streams for the telcos.
Ah, the business side.
Right. They can offer AI as a service, AIaaS, not just internally for their own customer service, network ops, marketing, fraud detection,
Right.
but also as a commercial offering to external enterprise customers who need edge AI capabilities.
So a telco could become a provider of both connectivity and distributed AI compute. That's a transformation.
It's the emerging picture, yeah.
Yeah.
We're already seeing major telcos offering Gen AI tools, LLMs, AI platforms built on their network infrastructure.
Any example?
Well, the Global Telecom AI Alliance, the GTAA, they're working together on a multilingual telco-specific LLM,
For what purpose?
primarily designed to improve personalized customer care, make those interactions better.
Very specific application. Are there broader strategies too?
Absolutely. Some operators are taking a more holistic approach, bundling Gen AI with their cloud and connectivity services. Maxis, for instance, partnered with AWS, offering integrated Gen AI and 5G solutions to businesses. It's about creating a suite of services, leveraging that combined communication and AI power.
Interesting. So the RAN becomes a versatile platform. Okay, third aspect, AI and RAN. What's the core idea here?
AI and RAN focuses on the efficiency side. How do you realize AI ran cost effectively? It's about dynamically sharing the underlying compute resources between the RAN network functions and the AI applications.
So instead of separate silos for RAN and AI compute,
Right.
they can borrow capacity from each other dynamically.
Exactly that.
Yeah.
Dynamic orchestration is the absolute linchpin here. The idea is to repurpose and share resources, CPUs, GPUs, memory, based on the fluctuating demands of both RAN and AI workloads.
Which should lead to better utilization.
Significantly better utilization, yeah, and lower infrastructure costs. You're not over-provisioning separate systems.
Can you give a practical example of how this dynamic sharing might work?
ARNA Networks has a platform called AMCOP. It gives a good illustration. It monitors the RAN's resource usage,
Okay.
and when it sees, say, GPU cycles sitting idle,
Which happens a lot with bursty RAN traffic.
it does. So AMCOP can dynamically reallocate those idle cycles to run AI applications. This can really boost hardware utilization, maybe from, say, 30–40% average with just RAN, potentially up towards near 100% when you run AI alongside it.
Wow, that's a massive jump in efficiency. Any other examples like this?
SoftBank announced something called AI Tray. It's a unified GPU-based infrastructure designed specifically for multi-tenancy running both AI and RAN.
Okay.
And it uses AI-based orchestration itself to manage that dynamic resource sharing, letting telcos run both types of apps concurrently on the same physical hardware.
Makes sense. AI and RAN is about smart real-time resource allocation for efficiency. Okay, so we have these three facets: AI for, AI on, AI and RAN. Now, what are the essential building blocks needed to actually make AI RAN happen? What are the key requirements, the enablers?
Okay, several critical components here. First off, you absolutely need accelerated computing infrastructure.
Beyond traditional CPUs and ASICs.
Yeah, the traditional RAN hardware, often ASIC-based or just CPU-based, it's just not cut out for the heavy lifting of AI workloads, especially training and real-time inference. More flexible, software-defined hardware accelerators. GPUs are the prime example right now. They can handle the parallel processing needed for both advanced RAN functions and those AI algorithms.
So GPUs become kind of the workhorse.
Pretty much, yeah.
Yeah.
A versatile workhorse. And the infrastructure has to support both offline cloud training for complex models and real-time, low-latency inference right at the edge.
Two different demands on the same hardware.
Exactly. You need that massively parallel processing for handling huge streams of real-time data, accelerating AI, accelerating baseband signal processing like massive MIMO beamforming, even things like integrated sensing and communication.
And fast connections between everything.
Yeah. High-speed, low-latency interconnects are absolutely crucial.
Okay, makes sense. Hardware needs a major boost in flexibility and power. What about the software side, the architecture?
That brings us straight to the second key enabler, a software-defined, cloud-native design.
Moving away from hardware refreshes.
Completely. That old model, upgrading hardware every few years for a new RAN generation, it's just not sustainable for AI RAN. You need to abstract the network functions, the NFs, from the hardware.
Through virtualization containers.
Exactly. Software virtualization and containerization. It gives you flexibility, portability, programmability. Much more agile.
So the core RAN functions baseband, scheduling, they become software apps running on that accelerated hardware.
Precisely. They're implemented as cloud-native network functions, CNFs. This means you can spin them up dynamically, update them easily, roll out new features quickly.
Without touching the physical boxes.
Right. And the cloud-native approach lets you scale resources elastically.
Wow.
Add or remove CNFs based on demand.
And this is where things like Docker and Kubernetes come in.
Absolutely central. CNFs are typically packaged as microservices and containers, managed by orchestration platforms like Kubernetes. This setup enables efficient multi-tenancy running multiple RAN and AI services side by side on shared infrastructure.
Okay.
And things like CI/CD pipelines become essential for rapid, automated deployment of updates and features.
Got it. Powerful, flexible hardware, agile, cloud-native software. What ties it all together? How do you manage this complex mix?
That's the third critical piece. Joint orchestration of communication and computing resources.
It's an overarching management layer.
Exactly. In this multi-tenant world where RAN and AI share everything, you need a unified orchestration platform to manage it all efficiently. It has to handle real-time, on-demand allocation of both compute resources, GPU, CPU, memory and communication resources, bandwidth, network slices, etc.
Based on what?
Based on real-time traffic, user demand, SLAs, service level agreements. It's a constant balancing act.
That's incredibly complex, ensuring quality for both RAN and AI.
It is tricky, yes. And the orchestrator also needs intelligence to decide where to run things. Maybe latency-sensitive tasks stay at the edge, while compute-heavy stuff goes to a central cloud if time isn't critical.
Okay.
And crucially, AI models themselves can be plugged into the orchestrator to help make smarter decisions about resource distribution, optimizing for power, efficiency, load balancing.
So AI managing the AI and the RAN.
In a way, yes. And elasticity is key. The orchestrator needs to scale resources up or down instantly, leveraging hardware tricks like multi-instance GPU, MIG, multi-instance GPU. It lets you partition a physical GPU into smaller, isolated virtual GPUs, so you can dedicate slices to RAN and AI simultaneously on the same chip.
Very clever. Okay, hardware, software, orchestration. What's the final piece?
The final key enabler is native AI support. Meaning AI capabilities need to be deeply embedded within the RAN infrastructure itself. Not just running apps on top, but integrating AI into the core decision-making processes for real-time intelligence, automation, optimization across all layers, network, and compute.
So AI influencing everything from the radio signals up to the high-level functions?
Precisely. From the PHY layer right up through RRM, mobility management, load balancing, scheduling, AI models should be able to coordinate decisions across layers for holistic end-to-end optimization.
And that needs data.
Lots of data. Robust data pipelines are essential to collect and process information from all the network elements efficiently.
Okay.
And a key concept supporting this is the network digital twin, the NDT.
A virtual copy of the network.
Exactly. A virtualized replica. It lets you collect data, run simulations, train and validate AI models, all without messing with the live network. It's a safe sandbox for testing and optimization.
Smart. De-risks things significantly. Okay, so we have the requirements, the enablers. With all that in mind, what does an actual AI RAN deployment look like? What's the reference architecture?
Well, the blueprint really focuses on high performance, scalability, modularity, reflecting that deep AI and RAN integration. You typically see standard data center racks.
Familiar hardware.
Right. Filled with AI RAN servers. These have a mix. CPUs, powerful GPUs, DPUs, data processing units for accelerating networking tasks, fast SSDs, all connected by a high-speed Ethernet switch fabric.
Okay.
Cloud-native accelerated compute is really the heart of it. Allows rapid deployment, flexible scaling at those telco edge data centers.
So leveraging data center tech, but placing it at the network edge.
Exactly. An end-to-end deployment involves, the radio units, the RUs out at the sites, connected via front haul to these AI RAN servers. The servers host the DUs, the distributed units, sometimes also the CUs, central units, maybe even core network functions depending on the setup.
Okay.
Then you have mid-haul, backhaul, maybe dedicated AI networks connecting everything out to the internet.
How is all the traffic managed within that setup? The RAN data, the AI data?
The networking fabric is kind of logically split. You have a compute fabric and a converge fabric.
It's compute and converge. Okay.
The compute fabric handles that high bandwidth, low latency front haul stuff. The raw radio signals between RUs and the servers, that's often called east-west traffic.
Okay.
The converged fabric carries the combined RAN and AI workloads between the AI RAN servers and the rest of the network, the internet.
Yeah.
That's more north-south traffic.
Got it. And the software stack running on these AI RAN servers, you mentioned cloud native.
Absolutely fundamental.
Yeah.
You'll typically find a cloud OS, like Kubernetes, providing cloud as a service, CaaS, managing the hardware, orchestrating the software components.
Okay.
On top of that, you have specialized computing platforms, like NVIDIA's CUDA for GPU acceleration, and networking platforms like DOA-CA for network offload. These run both the RAN and AI applications.
And how are the RAN parts and AI parts managed specifically?
So the RAN functions DU, CU, maybe CN are usually managed by an SMO framework, service management and orchestration.
SMO.
Right. And for the AI side, you typically have something like an API cluster agent managing the AI workloads within Kubernetes, their lifecycle resources.
So separate management planes, logically at least, but running on shared hardware.
Precisely. And often there's an overarching E2E orchestrator end-to-end. It sits above both the SMO and the AI agent.
What does that do?
Its job is crucial. It tracks overall resource use and coordinates both the RAN workloads and the AI inference requests happening on that shared hardware. Ensures efficient multi-tenancy, keeps everything running smoothly, meets the quality of service needs.
This all sounds incredibly powerful, very integrated, but also complex. Has it actually been demonstrated? Is there a proof of concept showing this works in reality?
Yes, absolutely.
Sure.
Our sources detailed a really compelling proof of concept. It showed you can run RAN and AI workloads together, concurrently, on the same hardware without hurting performance.
Multi-tenancy, as you called it.
Exactly. Whether you do it by time slicing the resources or dedicating portions using things like MIG, the key again is that intelligent orchestrator handling the provisioning, deprovisioning, shifting workloads dynamically.
What hardware did they use for this PPA?
They used NVIDIA Grace-Hopper GH200 servers. These are specifically designed for this kind of HPC and accelerated AI stuff.
Okay. And the scenario?
It involved a mobile user interacting with either a chatbot or, get this, a photorealistic digital human.
A digital human. Wow.
Yeah, all happening over a 5G network powered by NVIDIA aerial software. And the critical part, the LLM, the large language model driving the chatbot, and the digital human was running on the exact same GH200 server that was simultaneously processing the entire 5G RAN workload.
Whoa, okay, so one server handling real-time 5G radio processing and the heavy lifting for a generative AI model at the same time.
Exactly. The chatbot used a web browser, pretty standard. The digital human was more complex, needed real-time voice transcoding, high-fidelity rendering, video streaming, but all driven by the same underlying LLM.
An LLM trained on specific data?
Yeah, trained on relevant customer and telco data. And it ran without messing up the 5G RAN performance. They had a 4T4R 5G Node B running, 100 MHz bandwidth, 30 kHz subcarrier spacing, a proper setup.
So how did they partition the server resources? How did they make it work?
So the GH200 server had 2 GPUs. They used that MIG capability, multi-instance GPU, on one of the GPUs.
Okay, splitting one GPU.
Right. They carved out one instance using about 40% of that GPU's resources purely for the real-time 5G RAN processing.
Okay.
The other MIG instance, using the remaining 60% of that same GPU, was assigned to the AI workloads, the LLM, for the chatbot and digital human.
And the second GPU?
Completely free. By efficiently packing both RAN and AI onto one GPU using MIG, the entire second GPU was just sitting there, available for other tasks, other services.
That is a striking demonstration of better resource use. What was the bottom line on utilization?
Well, the experiment clearly showed significantly enhanced resource utilization. Running both together achieved much higher overall GPU usage compared to just running the RAN workload alone.
Which tends to be bursty, leaving idle capacity.
Exactly. RAN might peak around 40% utilization sometimes, but often leaves a lot of the GPU idle. By filling that idle capacity with AI, you maximize usage, minimize waste.
And that translates to cost savings.
Potentially significant reduction in total cost of ownership for operators, because they could maybe sell or use that spare GPU capacity for other services when network demand allows. Monetize the idle time.
That's a really powerful proof point. Concrete evidence that these diverse, demanding workloads can coexist efficiently on shared infrastructure. Okay, so as we wrap up this deep dive, what's the main takeaway message about AI RAN?
I think the fundamental takeaway is that AI RAN isn't just an incremental step, it's really a major evolutionary leap for mobile networks.
A paradigm shift, almost.
You could say that.
Yep.
By deeply integrating RAN and AI onto shared infrastructure, we're building networks that are way more adaptive, efficient, and, well, intelligent. These future networks can dynamically allocate resources, optimize themselves.
Getting diverse needs much better.
Right, meeting the needs of users, new services, maybe whole new industries that we haven't even fully envisioned yet.
And for listeners who found this fascinating and want to know where things are heading, what are some key areas of future work or research to watch?
Oh, several exciting directions. One is definitely building even smarter, AI-driven, closed-loop orchestration frameworks.
Making that management layer even more intelligent.
Exactly. Managing compute and communication seamlessly, factoring in latency, reliability, energy use, the whole picture. Another huge area is continued work on standardization and interoperability.
Open interfaces, common data formats.
Crucial for widespread adoption. Needs collaboration between standards, bodies, industry groups. Everyone needs to play nice together. And finally, we just need more real-world validation. Comprehensive test beds, solid benchmarking methods, field trials, pilot deployments.
Proving it works at scale, refining best practices.
Exactly, moving from proof of concept to robust, deployable solutions.
Fascinating areas to keep an eye on. So, to leave you all with a final thought, really consider how this fundamental convergence of RAN and AI, right at the network edge, could unlock entirely new categories of applications and services we haven't seen before. And maybe ponder, what are the biggest technical hurdles still standing in the way of fully realizing that potential?
Good question to mull over.
Thank you for joining us for this deep dive.